First of all, let me thank the organizers for the opportunity to give this talk. This will be a bit of a continuation of Misha's talk. I am not sure I will be able to see the chat while looking at my presentation. So if you have questions, just shout, just holler. Okay, since Misha gave all the definitions, I will go over them a bit more quickly. We have a finite set of points omega, and we have binary relations on them, and each binary relation has a corresponding adjacency matrix. And if F is a field, then we define 3 different products on the matrices, where rows and columns correspond to elements of omega. We have the usual matrix product. We have the Jordan product, and we have the Shor-Hadamard product, element-wise product. And if we have a linear subspace of matrices which is closed under the element-wise product, then it has a unique basis consisting of mutually orthogonal 0-1 matrices, and we call that the standard basis of this subspace. And yeah, if we have such a space, then each basis matrix is a 0-1 matrix, so it can be considered as the adjacency matrix of a binary relation. And we can switch between binary relations and matrices, and use whichever language is more convenient. Okay, this n there should be an omega. Now, if we have such a subspace, we call it a coherent configuration or coherent algebra. I use these words a bit interchangeably. If it contains the identity matrix and the all-one matrix, and it's closed on a transposition, the matrix product and the Hadamard product. And if we replace the matrix product with the Jordan product, we get the definition of the Jordan configuration, or Jordan scheme. By the way, I will restrict myself in this talk to symmetric homogeneous Jordan schemes, and will not consider them the more general case. So Misha gave this example on 15 points of a proper Jordan scheme. And I would like to give another illustration, another model of this, which may help to understand this. So we start with the alternating group A5 on the set of points 0, 1, 2, 3, 4, and we let it act on pairs of disjoint edges, so pairs of disjoint pairs, and we get an imprimitive action of degree 15, and the centralized algebra of this group is an association scheme of rank 6. We have 3 relations of valency 4. We have 2 non-reflexive relations of valency 1. And the symmetrization of this is a Jordan scheme of rank 5, and we have these relations which I write here in different colors. R0 is the reflexive relation. R1 is of valency 2, and R2, R3, R4 are distance regular graphs of valency 4. R1 consists of 5 triangles, so it's an imprimitive, strongly regular graph. Okay, and these distance regular graphs are really isomorphic to the line graph of the Peterson graph, which looks like this. And we have, well, 3 edge disjoint copies of this graph on the same vertex set, and sharing a, well, a common imprimitivity set, basically. So let's, we have these 5 triangles, and we pick one of them and call it the island, and we call the union of the other triangles the continent. And then within this triangle, within this island, all edges are in relation R1. And between the island and the continent, there are no edges in relation R1. And if we call these edges from the island to the continent bridges, then these are all in these relations R2, R3, or R4. And so we have this picture, 5 triangles, one of them selected arbitrarily. We have between, on the continent, blue, red, and orange edges between these triangles. And we have blue, red, and orange bridges between the island and the continent. And this defines us a Jordan scheme of rank 5. But it is improper since it is the symmetrization of this association scheme, which comes from A5. And now we do this generalized sidle switching, where we basically just interchange 2 bridges. We take 2 colors here. We fix one of the colors. I think we fix the red color, and we interchange the orange bridges with the blue bridges. Well, no, actually, we fixed the orange one, but doesn't make any difference. So we switch blue and red edges there, and we get a new rainbow, which turns out to be a proper Jordan scheme. Okay. If we take this rainbow and compute its the smallest coherent configuration that contains it, then we get rank 21, and that means its symmetrization has rank at least 11, and so it is not the same as our starting scheme, and so this is really a proper Jordan scheme. So we think that this is the smallest example of a proper Jordan scheme, symmetric, and I've been trying to prove this computationally, and it's still not quite done. But I described steps that I've taken so far in that direction. So we call a graph coherent if it is the basis graph of a suitable coherent configuration, and I will call it Jordan coherent if it is the basic graph of a suitable symmetric Jordan scheme. Well, why are these graphs interesting? No, first of all, we can see a connection between these two notions. Coherent graph is certainly Jordan coherent because here every coherent configuration is Jordan configuration. And a Jordan coherent graph is regular if it's the base graph of a homogeneous symmetric scheme. And since we want to find homogeneous symmetric schemes, we will only consider such regular Jordan coherent graphs. We can say more about these graphs. They're not only regular, they're even edge regular, which is not hard to see. And so this gives us one possible strategy for the enumeration of small Jordan schemes. First of all, find all edge regular graphs of order n up to isomorphism. From those, check each graph to see if it's Jordan coherent. And once we have all these Jordan coherent graphs, we know there are up to isomorphism all the basis graphs that we need. And so we need to put them together to form Jordan schemes. Okay, so we can look at these various steps one by one. As a little disclaimer, I will not look at all possible Jordan schemes. The enumeration of small association schemes has been done at least up to order 31 by Hanaki and Miyamoto. So what we really need to enumerate is only proper Jordan schemes. So we can discard certain cases where we know that there will be no proper examples. And so, as Misha said, if the rank of a Jordan scheme, of a symmetric Jordan scheme is at most 4, then we have an association scheme. So we may assume that the rank is at least 5. Now, how do we find these basis graphs? We know they're edge regular, and in particular, they are regular. And there is a very efficient program for generating regular graphs by Markus Mehringer. The program is more than 20 years old, but still works quite well. And we can check each of these graphs. We can generate all regular graphs, check each graph for edge regularity. This might be a waste because, well, most regular graphs are not edge regular, and the number of regular graphs grows really fast. But it works for these purposes, and we can quickly find all edge regular graphs by this approach. Well, what restrictions do we have on the valency of graphs? We've seen if the rank is at most 4, then the scheme is actually an association scheme. And if we know all but one basis graph, then we know the whole scheme, that because the remaining basis graph is everything that's not covered by what we have. And so we can, it's sufficient to look at all basis graphs except for the one with the largest valency, and this means that the valency can be restricted to n-3/2. And for graphs of valency 1 or 2, we know when they are edge regular, and if they are edge regular, well, they are actually also coherent. So if we look at the numbers here, we see that well, for n less than 10, we can see that there cannot be any proper schemes. And the number of regular graphs grows quite fast, while the edge regular graphs are few and far between. Here n is the order of the graph, and k is the valency of the graph. So we have found all edge regular graphs. Hopefully, otherwise let me know. We can do the same for Jordan configurations, and just a second. And if we take these edge regular graphs and look which of them are actually Jordan coherent, then we see the number is really, really small. And all of these graphs are not only Jordan coherent, but actually coherent. And I would be really interested in an example of a graph that is Jordan coherent, but not coherent. I have yet to see something like this, or a proof that they don't exist, of course. Maybe there's an obvious argument why they should not exist. So if we have these basic graphs, now we need to put them together in order to get a Jordan scheme. But no, we only know them up to isomorphism. So we still have to figure out how to put them together. Well, we can go into something which I call a minimal generating set. That's a set of a set of graphs that generates a scheme, and no proper subset does. And we can enumerate those, and we have to see how we can add a new graph to such a generating set in order to get a new minimal generating set for another scheme. And for that, we need to basically enumerate ways of fitting this new graph in there. And this comes down to an enumeration of double cosets of the two respective automorphism groups. And we check whether we get or we get a rainbow, and we check whether that rainbow then is a Jordan scheme. And these are the results so far. We get a certain number of Jordan schemes. Of those, most of them are actually symmetric association schemes. The others so far are symmetrizations of association schemes, and we do not find any proper schemes here. We know there is an example on 15 points, and the computation has not yet finished for the case n equals 14, but so far I have not seen any examples there either. So that is a bit the anticlimactic conclusion here. As an outlook, I think there should be a better way to go about this. And this is, well, we do not start from the basic graphs, but we start from the possible tensors of structure constants or intersection numbers. We first of all can enumerate these tensors. And then for each of these tensors, we have much more information, and then we can try to enumerate schemes based on these tensors. But this is under development, and that is maybe a topic for another talk. My apologies for these technical difficulties. Once more, thank you to the organizers. And here are some references. The classification of association schemes, the fast generation of regular graphs by Mehringer, and then the two preprints that were already mentioned in the previous talk. Thank you very much.
Oh, dear Sven, thank you very much. Thank you. And are there any questions to Sven? Or any comments? Well, okay, let us thank Sven again. And I hope that next time you will give us another talk on the problem which is still under your consideration.
Yes.
Yeah, thank you very much. Well, actually, oh, sorry, actually I have one small question. You mentioned that you needed to get all minimal generating sets, right? Yeah, so you use it.
I would not,
right, yeah.
I do not strictly need all minimal generating set, but if I have all minimal generating sets, then I get all schemes.
Oh, I see.
Right, because a scheme may have several minimal generating sets.
Right, so you don't need to get all of them.
Well, in order to make sure that I get all schemes, I will. That would be my strategy, to get all minimal generating sets.
I see.
And then afterwards do an isomorphism check to get rid of duplicates.
I see. I see. Okay. 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 Thank you. Thank you very much for your talk and for your answers.